Hello everyone, this is Group 1's final project presentation of the cordless handheld vacuum cleaner. Here we have our product specifications listed, including battery power, weight, and annual estimated demand and production volume, as well as our primary and secondary customers.
In our FA diagram, we made sure to capture the function while keeping our design freedom.
And this is our new function component mapping matrix, which now has 14 parts instead of the old 15, because we combined the silicone nozzle and no cup into one part.
Our exploded view of the assembly. Our quad chart mapping functions to economics redesign with our criteria top left.
In this section, I'm showing how we translate the customer needs into our product architecture. In the column on the left of the functional differentiation table are essential functions everyone expects: lifting the surface debris, holding it, reducing noise, and ensuring convenience. These are all the must-haves. And on the right, for our professional users, we're really boosting the vacuum's capability. This means significantly more cleaning power for tougher jobs, enhanced filtering with the HEPA filter, and the ability to work longer and handle more debris without interruption. Essentially, it's built to meet demanding professional standards. Looking at our component commonality table, it shows how we build this efficiently. The platform components on the left, like the housing, interlock, lock pin, power switch, handle, motor housing, and charging point, are shared across both versions. This common base streamlines manufacturing and reduces manufacturing costs. The modules on the right are our key differentiators. By swapping out the motor, fan, dirt cup, filter, and silicone nozzle, we tailor each vacuum. This modularity allows us to offer a high-performance professional variant and a cost-effective household model, all from one smart design foundation.
Stemming from our product family design, here are different variants for the dirt cup and nozzle for different customer groups. Here's the common interface for the dirt cup and nozzle modules, as well as the modules for the motor, fan, and filter, which would have a motor have a higher RPM, filter have a higher MERV and HEPA ratings, and the fan would have a greater CFM. Here's the common interface for the filter. Looking at our pre-DFA analysis, our overall assembly time is 96.01 seconds with overall assembly efficiency of 31%. Based on these figures, the dirt cup and nozzle and interlock head were all combined into one part, as well as the motor housing and locking pin receiving redesigns. For our module redesign, we combined the dirt cup nozzle and interlock head into one part, achieving DFA 1, DFA 2, and DFA 7. An extra feature was added to aid in the connection between the dirt cup and the motor housing, achieving DFA 10 and DFA 11. Platform redesign included the locking pin being adjusted to have a protruding piece, as well as an embedded space for the dirt cup's lock-in piece at its bottom edge, achieving DFA 3, DFA 7, and DFA 11. Motor housing redesign included removing the sliding slot and having the handle snap into the motor housing, achieving DFA 1, DFA 12, and DFA 13. Post-DFA analysis shows an overall assembly time of 64.13 seconds, 33% drop, as well as an overall assembly efficiency of 47%. By redesigning the dirt cup nozzle and interlock head to be one part, this creates more ease for cleaning, part replacing, and assembly. As well as the locking pin provides a more secure link between the dirt cup and the housing. Consolidation of parts allows for a much faster and simpler assembly process, as well as ease with manufacturing.
The housing assembly was selected because the quad chart analysis flagged it as significant. All the parts underwent changes under DFA 6 for easier assembly from orientation. The housing had a change under DFA 10 with a chamfer allowing for easier snap fit from the insert. The power switch had a change under DFA 8 for less tangling by removing previous convexity. Although there was a drastic change in overall shape, all the parts return their primary function. The handle does lose the ability to slide, but a net positive, reducing cost by design. It's easier to orient, it's easier to assemble, it's cheaper. Through analysis of DFAA, total cost per assembly does go to 1/8 of its original price, which is great for the producer and consumer.
And the two parts that I chose to analyze for process selection are the lock pin and combined dirt cup and nozzle. For the lock pin, you want this to be made out of some sort of metal. I chose 303 stainless steel because it's just generally easy to machine. And yes, we're going to machine this, presumably using a CNC machine. The critical dimension here is the diameter of the locking shaft, because we want to make sure that it's not too small or too big, because we want the motor housing and the dirt cup and nozzle to fit appropriately. So we want to have a tight tolerance of around 5/10,000ths of an inch. That's what I chose. And for the combined dirt cup and nozzle, We want this to be made out of some sort of plastic. So I chose a cheaper one, polypropylene, so that's easier, cheaper to make many millions of these units. And we're using injection molding because of that for a manufacturing process. And the critical dimensions here are the nozzle outlet size and mating edges, because again, we don't want that to be too big or too small. And we want to make sure for the nozzle outlet that it's the appropriate size, that enough air can be sucked in. So we still want a tight tolerance, but not as tight as the lock pins. We want that to be about 5/1000ths of an inch.
Here is our polypropylene dirt cup nozzle. Before any changes, we were paying 78 cents a part across a 50 million unit program. Looking at the purple faces, DfM Pro flagged those broad, unsupported panels as part of our DFIM1. They were causing warp and longer cooling. We added lightweight reinforcing ribs and in the walls uniformly. That cut material cost by about 20% and shaved cycle time. Material drops to 26 cents, operating to 33 and mold staying at 5 cents. Net result is 64 cents per part, which is 14 cent savings, or roughly $7 million in the long run with no impact on fit or function.
Now we're going to talk about our design for manufacturing of our lock pin design. So we started by putting our previous design into DfM Pro and entering our parameters such as our stainless steel material, our volume, mass, and our tolerance. And from there, DfM Pro was able to highlight two main issues. The first issue was the wall thickness, and the second issue was the minimum draft. And these are two issues that are pointed out by the pink lines in the pictures. Now, the problem with these issues was that the extra thick sections and the near zero draft angle was driving both the material weight and our machine cycle, which was making things more expensive. So the way that we handled these issues was by trimming the walls by around 20% and opening the draft to 2 degrees. And then we also added some supports to the large faces. So this dropped the material cost from about $8.78 to $7.05. So the overall total cost we were able to cut down from $10.08 to $8.15. So in total, saving around $1.93 with our DfM Pro analysis of our lock pin design. Next, we completed a hubs analysis of our before and after design. So we plugged in all of our parameters, and I put in for the quantity of 50, 100, 125, and then from there I was able to create an extrapolation curve and took 8% of that at the 50 million quantity, and I was able to get this 58 cents for the before design, 17 cents for the after design, and around 41 cents saved from the before and after. Now, compared to the analytical, there's $10.07, $8.15, and $1.92. So if you notice some kind of discrepancy, that's most likely because that once you get to the 50,000 quantity number, Hubs does not go there. So when you extrapolate at this region, there might be more error with extrapolation.
To enhance the vacuum cleaner experience, we designed a mobile app concept called Vacuum Clean. This app connects to the vacuum via Wi-Fi and provides a smarter, more interactive user experience. Key features include usage analytics to improve cleaning habits, maintenance reminders to notify users when to clean filters or empty the dust cup, easy replacement ordering, and battery monitoring. The idea is to reduce downtime and extend the vacuum's lifespan while also adding convenience, especially if helpful for users who rely on it daily, like rideshare drivers or pet owners. This concept could also open new revenue stream through subscription model, offering upgrades or auto replacement. Most importantly, it supports sustainability by reducing waste and encouraging routine upkeep. We achieved strong improvements in both assembly and manufacturing. Manual assembly time dropped by nearly 32 seconds, and we reduced cost in both plastic and metal parts. We did face a few challenges. Refilling the dust cup still feels awkward, and some cat dimensions didn't translate well to real-world use. The simplified face plate also raised some durability concerns. Moving forward, we plan to refine the electrical layout, remove unnecessary structures like the motor mount, and improve parts interfaces. We also see great potential in fully developing the smart app to support the product service system. Thank you for your time to review our presentation. We appreciate your attention and would be happy to answer any questions.